Sometimes when we are doing physics, or maybe I should say when you are doing physics, because I don't really do physics, maybe you want to find out how much acceleration is acting in the direction of motion. And that's what the tangential and normal components of the acceleration is for. In this video, our goal is to see how to write A as two components. The first part is some number AT times the unit tangent factor, and the second part is some number AN times the unit normal factor. We're going to figure out a formula for this and also for that. And first, let me just give you guys a quick picture. Let's say here is our position, R. So for t, let's say we have the unit tangent factor right here. And because it's a unit factor, so the length of this is just equal to 1. And then once we have t, we can say here is n, it's normal to this, and it also has length 1. Alright, now we have at times t. So I'm just going to say, maybe it's longer like this. So here is at times t. And then for an times n, I will just put it up like this right here. So this is an times n. Now we want to combine this and that together to get a. How? Well, just do the addition of two factors. Use the parallelogram method. I'll put this one right here. And then I'll put this one right there. And then just connect the diagonals, right? From here to here. And this is where the acceleration factor is pointing. So now let's go ahead and just do some math to figure this out. We are going to first start with a curve, of course. So I will just say, here's the work given r. What we need first is the velocity. By definition, this is the derivative of r with respect to t. Now, we have to think about how can we squeeze out the capital T, the unit tangent factor. Remember, let me just put this down right here. For the unit tangent factor, the definition of that is dr, but you take the derivative of this with respect to s. Here we have dr already, but this is unfortunately with respect to dt, right? But it's okay because we can use the chain rule. So we are going to look at r, take the derivative of that with respect to s first, and then look at s, take the derivative of that with respect to t, and this is just the chain rule. So thanks to this right here is just going to be our capital T, the unit tangent factor, and then we multiply by ds dt. And remember that this right here is the speed, right? It's the change of arc length over time. Just imagine you have the total distance traveled divided by time. So that will tell you the speed. So once we have the velocity, next we are going to get the acceleration by differentiating the velocity. So check this out. A is equal to the derivative with respect to t of our velocity. So I'll put down phi. And phi is exactly that. So we are going to differentiate t, and this is just multiplication with ds dt. Now, this is a product. We still have to use the product rule. Here we go. I'm going to keep the first function. I will just write that as t, and then I will differentiate the second with respect to t. So we get what? The second derivative of s with respect to t. So here, d2s dt2. And then we add the second function. Let me just put that down first. And then we multiply by the derivative of the first one. So that will be dt dt. And this right here is just a regular multiplication. So the order of it doesn't matter. It's not a cross product. So we are good for that. Okay. We have t. That's the t component that we want. But we also have to squeeze out the n. So how can we do it? Well, remember n is equal to 1 over kappa, the curvature, times dt and what? ds. Yeah? In fact, kappa is the length of this thing. So that's how we can make this a unit vector. Multiply kappa on both sides, we can see that dt ds is equal to kappa times the unit normal vector. This is dt dt. We don't want that. We want dt ds, so we can introduce our vector n. So what do? Yes, of course, the chain rule one more time. So let me just put a note right here on the side for this part right here. So I'll just say note. dt dt, which is equal to dt. Do it with respect to s first, and then look at ds, and then differentiate that with respect to t, thanks to the chain rule. And then this part is exactly that. So you can say that it's kappa times n. And then right here, we have ds dt. And that's exactly what we are going to use right here. So this is going to be t, and then we have d2s dt2 plus ds dt times kappa n and also ds dt. Whew. Now, clean things up. This right here is exactly what AT should be, right? And let me write that down first. ds with a 2 right here, and then dt2 times t. And then right here, we have the n. Let's put that at the end. Notice here we have ds dt twice. So this right here is going to be ds dt squared. Here we also have the kappa times ds dt squared. Notice this is the second derivative, but this right here is the first derivative, but you square that. And then at the end here, we have the n. So ladies and gentlemen, this right here is what AT is, and this right here is what AN is. So let me write it down right here for you guys. AT is equal to that. D2S, DT2. But what exactly does this mean though? How can we find this? Well, this right here is just taking the derivative with respect to t of the first derivative of s with respect to t. What's this? This right here is the speed. So we can write this down as dt ddt of the speed, which the notation is the magnitude of the velocity. So that is what we should use for finding AT. And then secondly, to find AN, this right here, it looks like we need the curvature kappa first, and then we multiply by ds dt, and then square that. But ds dt is the speed, so I can write that as kappa times the speed. I will just write it as this, and then we square that. Okay, so perhaps this right here will be the useful one. Likewise, this right here will be the useful one. Technically not really, because it's not easy to find kappa, right? But for now, AT is equal to this, AN is equal to that. Is there a better way to find out what AN is though? Yes, AT not so bad, right? Not so bad. But AN, we actually have way to avoid finding kappa. So let's see how we can figure that out. I'm going to erase this right here real quick. Now check this out. We have A is equal to this now. I am just going to do the factor A with the dot product with itself. So this right here will tell us we get the magnitude of A squared. And this is just going to be a number. But if you look at this, you can take this and then dot itself, right? And I'll tell you, in fact, what we are going to get is this being equal to this thing squared, so AT squared plus this thing squared, AN squared. And of course, you can just really dot this out real quick. So I will show you guys that this is correct. So AT T plus AN N, and then if you dot this itself, right, AT T plus AN N. All right, so I'm going to just distribute like this, right? So as you can see, we get AT times AT, and that's AT squared. And then we will have this dot this. So it's T dot T. And then next, we'll have this times that, right? So that's plus AT times AN. And then we have T dot N. And then I will have this times that. So we will have AN AT and then N dot T. And then finally, this times that, which is AN squared and then N dot N. Now, what's this? What's T dot N? Well, T is right here, N is right here. They are normal to each other. So the dot product of it will be 0. So this right here is gone. Likewise, this right here will also be gone. And what's this? T dot T is just the magnitude of T squared. And T is a unit factor, so this right here is equal to 1. Likewise, this right here is also equal to 1. So in the end, we just have AT squared times 1 plus AN squared times 1. So if you want to work it out, this is it. But as a result, you get this right here. All right, so what we have now is this is equal to that. And let me just write this down right here like this. And our goal is to figure out what AN is, right? So let's move this to the other side, but I will write this down first. AN squared equals the magnitude of A squared minus AT squared. And then right here, I just have to get rid of the squared. To do so, take the square root on both sides and make sure you just do it with the positive square root. Because remember, this is what N is pointing. You want to have positive value for AN so that you have the same direction going this way. So you take the positive square root and you will get AN equals square root of the magnitude of A squared minus AT squared. And this right here, it's a better formula compared to that because right here, we do not have to find the curvature first. So this right here are all you need for the tangential and the normal components of A. And in the next video, I'll show you guys an actual example.